Alors, on peut peut-être commencer. Alors, aujourd'hui, pour le séminaire du CeRVIM, c'est Kefei Wen, qui est un étudiant au doctorat au laboratoire de robotique, qui a accepté de faire une présentation. Et Kefei travaille sur les manipulateurs parallèles hybrides cinématiquement redondants, plus particulièrement pour l'interaction physique humain-robot. So 2 weeks ago, Kefei presented a paper in an international conference, which was the International Workshop on Parallel Mechanisms and Manipulators. And I would like to point out that this was the 4th edition of a symposium that we started here at Université Laval in 2002. So there was a 2nd edition in 2008 in France, in 2014 in China, and this year it was in UK. However, it was online, of course, because of the present situation. So Kefei presented his paper at the conference. So today he will present an extended version of that presentation, I think a little bit extended to give more background. So I would like to ask everyone, ou tout le monde, si vous voulez éteindre vos microphones, je pense que pas mal tout le monde le fait pendant la présentation. So Kefei, please, you can go ahead.
Thank you very much. I will share my screen with you. Okay. So, can you see my screen?
Yes.
Okay, very good. Thank you very much. So, good morning, everyone. I'm Kefei Wen, and I'm currently a PhD student under the direction of Professor Clement Gosselin in the Robotics laboratory. And welcome to my presentation on workspace enlargement and joint trajectory optimization of a 6+3 degree freedom kinematically redundant hybrid parallel robot. This is the content. First, the architecture and the kinematics of a novel 6+3 degree freedom kinematically redundant hybrid parallel robot will be described. And in section 2, the results of translational and orientational workspaces will be provided. And in sections 3 and 4, approaches for workspace enlargement and for joint trajectory optimization will be developed and discussed, and finally conclusions are addressed. These figures show 2 examples of kinematically redundant serial robots for physical human-robot interaction. The kinematic redundancy is exploited to avoid singularities. However, these serial robots have some limitations, such as high inertia due to the moving motors and high inertia ratio, high gear ratio in the motors. Therefore, force torque sensors are used to make them backdriveable. Because of this, these robots can only produce a very low physical human-robot interaction bandwidth. By contrast, we propose a novel 6+3 degree freedom 3 RR-RRR kinematically redundant hybrid parallel robot. The robot here, R denotes a revel joint and S denotes a spherical joint. The robot has 6 Cartesian degrees of freedom, which are the position and orientation of the moving platform, and 3 local degrees of freedom, which are the direction of the redundant SR links. And here they are denoted as angle beta I. And the dimensional parameters of the robot are given in the table. Here, RB and RP respectively denote the circumradii of the base and moving platform. And the angle beta I is initially and arbitrarily chosen as 97 degrees. The axis of the RFO joint is parallel to the Z prime axis, and which is orthogonal to the plane of the moving platform. In each leg, It has 3 actuators. These are the velocity equations. The velocity equations can be obtained by differentiating the constraint equations with respect to time. Here, the dimension of the Jacobian G is 6 by 6, while the dimension of the Jacobian K is 6 by 9, because we have 6 Cartesian coordinates, while we have 9 joint coordinates. The Jacobian G is composed by 6 particular lines, where each 2 lines in a leg intersect at the strike joint. The particular line I1 passes through both joints SI and RI4, while the particular line I2 is parallel to the axis of joint RI4. Type 1, there are 2 types of singularities. Type 1 singularity may occur when the strike joint SI lies on the axis of RI1 joint, or when the serial chains RI1, RI2, RI3, and SI fall extended or folded. But these singularities, we don't need to avoid these singularities because they occur only on the boundary of the workspace. The figure shown in the lower left corner is a top view of the moving platform of the robot. Here, the lines I1 are coplanar lines, which are represented as dashed lines, while lines I2 are parallel in space and represented as solid circles, and they are orthogonal to the paper. There are 3 conditions for the type 2 singularities. First, the lines I2 become coplanar parallel, which are the solid circles, but these are readily avoided because we can, in the design, we can make the redundant SR link very short so that we can make sure these 3 lines never parallel to each other. And the other 2 conditions are the lines I1 intersect at a common point, or they are parallel to each other. These are also readily avoided because we can actively control the direction of these three lines, which are determined by the redundant degrees of freedom beta I, which in turn, which is to say we can actively control the redundant degrees of freedom. In the final design, the second and third links of a leg is replaced by a planar file bar mechanism, so that we can mount the second and third motors as close as possible to the base as close as possible to reduce the inertia of the moving part. And in order to make the opening and closing motion of the gripper along a straight line, we replace the redundant SR link by a parallel grind. And the kinematic redundancy is further exploited to operate the gripper as a moving platform from the base actuators. This architecture exhibits several features. For example, the robot is completely singularity-free throughout the workspace. Therefore, it can produce a very large orientational workspace. Because angles, the redundant coordinate angles beta I can be controlled actively, we are able to obtain an analytical inverse kinematic solution. And direct drive actuators are used. Therefore, the robot is easily backdriveable, and no force and torque sensors are required during physical human-robot interaction. Because the robot has low inertia, lightweight, and low impedance, it can produce a very high physical human-robot interaction bandwidth. And by the way, this architecture can produce the same translational and orientational workspaces as the 3 RRR SR1. This video demonstrates the excellent rotational ability of the architecture and physical human-robot interaction. It can be seen that the motors undergo motion with just a small amplitude, and the interaction is quite effortless and intuitive, thanks to the very low moving inertia, and thanks to the backdropability. This figure shows several layers of the translational workspace evaluated with beta I equal to 97 degrees. Here we assume that beta 1, beta 2, and beta 3 are the same. It can be seen that the workspace, the translational workspace, is almost convex, except several layers near the base. By contrast, the translational workspace of its non-redundant counterpart might be split into different regions due to the type 2 singularities. And the size of this translational workspace will not be a concern because it can always be enlarged by scaling up the robot. The figure on the right shows the very large orientational workspace evaluated with beta I is 97 degrees. The workspace is represented by tilt and torsion angles using cylindrical coordinate as that shown in the figure on the left, in which the vertical line, the vertical axis represent the torsion angle, while the radius of the circles represent the tilt angles. It can be seen that the maximum tilt angle can be larger than 135 degrees. But the maximum tilt angle of its non-redundant counterpart proposed in this reference is limited to approximately 40 degrees due to type 2 singularities. In this section, we consider 3 ways trying to enlarge the workspace. For example, we consider selecting different magnitudes of angles beta I and different lengths of RFO and different length of the combination of RP and RFO, where the magnitude of RFO is computed by this relationship. Also, in order to determine the optimal value of these terms, we define 3 performance indices, where the first 2 indices are the kinematic sensitivities, which are respectively the 2 norm of the position part and the 2 norm of the rotation part of matrix U. While the third performance index is the condition number of a novel Jacobian, Jn, and in which the matrix Mi is the Jacobian of the SRRR robot lag. The Jacobian Jn maps the joint acute joint velocities to the velocities of 3 different points on the moving platform. In this case, the 3 different points on the moving platform are selected as the center of the spherical joints. However, a computation over the whole workspace is time-consuming. Therefore, we just reassess several portions of the workspaces. For example, for the translational workspace, we reevaluate the layer of Z is 350 millimeter, while for the orientational workspace, we reevaluate the layer of C is 0 degrees, of 0 degree. As can be seen in the figures on the left, we replotted several translational and orientational workspaces with respect to 4 different angles of beta I. Although we can plot the workspaces for other angles of beta I, but we just replotted 4 of them for simplicity. And let's take a look at the x-axis of the translation workspaces and the direction of gamma equal to 0 degree of the orientation workspaces. The figures on the the figures on the right show the maximum translation and tilt angle and the corresponding performance indices computed with respect to angles beta I over the range of 55 degrees to 180 degrees. It can be seen that for this specified directions of the translation workspace and orientation workspace, the approximate optimal value of beta I could be 140 degrees, because as can be seen here, if the angle beta I exceeds 140 degrees, the performance index at 2 is going to increase, as can be seen here and here, while the maximum tilt angle is going to decrease, as can be seen in this figure. And similarly, the approximate optimal value of the length of the redundant link LFO could be 160 millimeter, because in this case, if it exceeds 160 millimeter, the performance index at 3 is going to increase significantly. So by the way, we should admit that these performance indices should be as small as possible. Otherwise, the robot will be very close to a singularity. And finally, let's take a look at the x-axis and the direction of gamma equal to 0 degree. It can be seen that the approximate optimal value of RP, which is the circumradius of the moving platform, would be 200 millimeter, because if this value is higher, the maximum translation workspace will reduce significantly, and the performance index at 3, as shown in the bottom right corner, is going to increase dramatically. By the way, we can see that here from all of these figures, we can see that the enlargement on the translational workspace is in fact limited. However, the enlargement on the orientational workspace can be is very large in certain directions. In this section, we will discuss the possibility to optimize the joint trajectory. In general, the inverse kinematics of kinematically redundant robot is solved using the numerical solution at the velocity level. And the last term shown here is used to minimize the performance index eta. However, this solution has several drawbacks. For example, the convergence must be guaranteed, and the initial configuration should be prescribed, and the solution may suffer from the repeatability problem. But in our case, because that the redundant degrees beta I can be actively controlled, so we don't need to use the numerical solution. But the problem is how to determine the how to minimize the performance index eta, because we have infinitely many combinations of beta 1, beta 2, and beta 3. Here, again, a computation over the whole workspace is time consuming. So we just consider only one trajectory, which is given here. Assume that the platform, the robot, translate from x equal to 0, y is 0, and z is 350 millimeter. 2x is 350 millimeter, and y is 0, and z is 350 millimeter. For each value of x, which means for each step of x, we compute the minimum of the aforementioned performance indices at 1, at 2, and at 3, with respect to beta I over the range of 50 degrees to 175 degrees. And we assume that beta 1, beta 2, and beta 3 are the same all the time in order to reduce the computing time. And the optimal value of beta I will be the one that the corresponding index beta 1, beta 2, or beta 3 is minimized. Here, the range of beta I is chosen based on the consideration that no singularities or mechanical interferences between the redundant links and the moving platform will occur. And the calculation interval of beta I is said to be 1 degree. As can be seen in the figure on the left, right, the covers of the minimum at 2 and minimum of at 3 are pretty good, but the results of the minimum of at 1 are unacceptable because in this configuration, which is when x equal to 277 millimeter, the angles beta I should decrease abruptly to minimize the performance index at 1. This is because, as can be seen in the figure on the right, so for each value of at 1, although we divided this at 1 by 100, but this represents the same thing. For each value of at 1, in fact, we have two local minimum, and of course, we have only one global minimum. And this abruptly change is caused by the shifting of the global minimum at around x equal to 277 millimeter. However, we have two possible methods to avoid this rapid decrease of beta I. The first method is we just compute the minimum of performance index at 1 with respect to a smaller range of beta I, for example, 140 degrees to 175 degrees. In this case, the result of this method is shown here. We can see that here the result is very small. And the second method is we filter the angles beta I, filter the angles of beta I using exponential smoothing. For example, the equations for the exponential smoothing is are given here, and we can see that we should be careful when choosing the smoothing factor of alpha, because if alpha is too large, the results shown here will be very close, very similar to that shown on the left. And here we can see that if alpha becomes smaller and smaller, the results of method 2 will be very close to the results of the method 1. The optimized robot has many potential applications. For example, here, this figure shows an intent application of the robot in an upside-down configuration in a macro mini system. And by the way, two relevant videos has been uploaded to our lab's YouTube channel, and welcome to watch for them. Finally, we'll come to the conclusions. We can see that the workspace can be further enlarged by the redundant parameters, because the redundant parameters for example, the redundant angles beta I or the length of the redundant links are easy to handle in practice because they are not connected to the motors. And although the enlargement of the translational workspace is limited, the orientational workspace can be improved significantly in certain directions, which can be seen in the result in the plots. And finally, the joint trajectory can be approximately optimized without having to resort to numerical algorithms, because as it is seen that the inverse kinematics can be solved analytically. Okay, so finally, thank you so much, and I'm happy to answer any questions from you.
Thank you very much, Kefei, for the nice presentation. If people have questions, you have two options. You can turn on your microphone and ask the question directly, or you can use the chat. But since there's not that many people, I think you can turn on your mic and ask the question directly to Kefei. Maybe I can start with the first question.
Yes, yes, please.
We can see from what you've done that there are two types of optimizations that can be done. One is at the design stage, where you select, for example, the link lengths and so on, in order to maximize the workspace, for example, and keep good conditioning indices. And another one is when you operate the robot. So you optimize the configuration of the robot, the redundant parameters, such that you can maximize the workspace, or you can maintain, you can stay away from singular configurations. One question I had was, when you did the analysis and the graphs that you showed, did you consider the mechanical interferences when you established the workspace, or it was just the kinematic limitations?
So do you mean here when I was evaluating the workspace, or during the optimal design stage?
Both.
Yes, yes. I have considered the mechanical interferences. In this case, for example, excuse me. So when I was evaluating both the translation and the orientation workspaces, of course, the singularities are exclusive. We don't have singularities, and for mechanical interferences, I assume that for each non-connected links, I assume that I set minimal distance between them, which is around 20 millimeter. So for each step of evaluation, I compute the minimum distance between each two links to see whether they will interference or not. And using this way, I can make sure that the mechanical interferences have been taken into consideration. And in this case, when so during the optimization stage, I said that the range of beta I being to 55 degrees to 165 degrees. In this case, all of the mechanical interferences has been taken into consideration.
Okay, thank you. Because since the robot is essentially singularity free, then mechanical interferences are the main limitation that we should consider. So that's important.
Exactly.
Yeah. Okay, maybe other people have questions. Feel free to speak or to write in the chat. There's a question from Vincent. Is there a special transition between control mode or human control mode? Maybe that's a question for C, actually.
Exactly, I see.
Maybe C, you want to answer that?
Yeah, so let's see.
So how does the robot know that the human is trying to take control of the end effector? I guess this is the question.
Yeah. So maybe I can answer simply by a simple way like this. So we have a robot with a really high back drivability. It means that every motion from the end effector, from the platform, we can detect, we can send, we can feel it directly on the joy angle. That's why when the human interact with the robot, we can detect that motion from the joy angle, and another reason that when we have the controller on the robot, we know that the maximum error on the joy angle, and that's why when we have the interaction from the human, it's over that error, and then we know that when the human wants to interact with the robot. Maybe that's the answer.
So essentially it works with thresholds.
Yeah. So the controller, we know that we have a threshold, we have a maximum error that we can handle, and with the external disturbance. That's why when it's over that's the error, so we know that we have an interaction from a human.
Yes, and at the same time, when the human stops interacting, when the end effector is no longer moving, then velocity is below a certain threshold, then you know that the person has stopped, right?
Yeah.
So Vincent, does that answer your question? He says, yes, thank you. Maybe other people have questions?
I'd have a question. Do you hear me?
Yes.
Okay, hi everyone. Bonjour. So my question is, you showed us 3 performance indices, and I was wondering, what I understood is you didn't consider, let's say, the width of your of the links or like some mechanical elements like this. So how scalable is the use of these performance indices when considering, like, let's say, the width of the bars of the links? Can you still use these indices, or like will you have to add other indices for the optimal workspace design?
No, we only use these 3 indices. So
okay.
As can be seen here, you mean the length of the redundant link SR link.
And what's that length? I didn't really catch that.
Yeah, no. So RR-RRR is here can be seen the.
Okay.
RR-RRR is the length of the redundant SR link, and RP is the circumradius of the moving platform.
Okay.
We chose this parameter because, as can be seen here, these links and the moving platform are not directly connected to the actuators. We can readily change their dimensions in practice. And here, how to determine the approximate length of RR-RRR is given in this figure. So, in fact, this is not the whole workspace of the robot, but we only we only re-evaluate some layers of the workspace, because the computation of the whole workspace is very, very time consuming.
Mm-hmm.
And for this one, for example, in these translational workspaces, we plot these workspaces with respect to different. Excuse me, I will show a slide. We replot these workspaces with respect to different lengths of the SR links, and then we just take this as an example. So we don't to find the global optimal value of the length of RFO. We just take this as an example to show that potentially we are able to enlarge the workspace. So let's take a look at the x-axis of this layer. You can see that, of course, we can plot other workspaces. They might be smaller than the one shown here. So we look at here, and we look at these four values. They are mapped to here, to this figure. And the performance indices are also plotted here. And we can see the different lengths of RFO. The RFO spans a range of from around 50 millimeter to 170 millimeter. So we can see here, we choose the optimal value of the length of RFO based on the performance indices. And we see that the translational workspaces increase gradually, and the performance indices looks pretty good. But if we look at the orientational workspace, we can see that if the length of the RFO is around 160 millimeter, the performance index at 3. The at 3 is as can be seen here, is this one is the condition number of this matrix. We know that if a condition number of a matrix is become very large, probably the matrix is EU conditioned and the robot is close to a singularity. And in this case, if condition number of Gn is very large, that means the robot is very close to a type 1 singularity. And we can see here the condition number, the performance index at 3 is going from around 5 to an increase to much larger than 20. So in this case, we can see that if the length of RFO is larger than 160 millimeter, when we evaluate the orientational workspace, the robot is probably in a type 1 singularity. That's how we determine the optimal value of RFO based on the performance index.
Okay, thank you very much.
Thank you.
Thank you. I was wondering who the mysterious iPad person was.
I didn't, sorry, I forgot to put my name. Okay. Okay. And so just for our last question, so which of these performance indices would be the closest indicator of, let's say, the surface area of the orientational workspace? You understand what I mean? So let's say you want to maximize the surface area, let's say for a certain layer,
yes,
you would like to optimize the surface area. Now, let's say this graph, you want to optimize the surface area of, let's say, one of the shapes. And
yes,
let's say you want to optimize this. Which of the performance indices would give you the best indicator of this optimization?
It depends on which one we are looking at. For example, when we evaluate this workspace, we look at all of the 3 indices, and we choose which one is critical. And as can be seen here, for the translational workspace, the indices at 1 and at 2 are quite small and stable. although the indices index at 3, the value of index at 3 is very large, but it's fine because the index at 3 indicates the robot is close to a tap point singularity. Of course, when near the boundary of the workspace, the robot is always in a tap point singularity. And here we look at all of these three indices, and we see that when we evaluate the orientation workspace at this point, the performance index 3 is going to increase abruptly. So in this case, performance in index at 3 will be in dominant. But in other case, for example, when we consider different magnitude of beta I, probably the performance index at 2 will be critical, as can be seen here and here. So the answer is, in fact, we consider all of the three indices.
Thank you.
Thank you.
Okay, but just I just want to support some point here in for Kefei, because the optimization based on these indices, it's at your point like mechanical design point, but for me, like at the control point of view, it's also really important. For example, like the third index, I think this relate to the configuration of the leg, and I can see it's really clearly that when the leg come to the really I would say a hard configuration where the sensitivity of that configuration really high, and it's very hard to control at that point. So
exactly, because as you said, the index at 3 is going to indicate whether the robot is close to a tap point singularity. In your case,
yeah.
You said it is very hard to control in that configuration, because in that case, the leg, one of the legs is almost fully extended or folded.
Yeah,
that's
yeah.
in fact
So
the tap point singularity. That's why it is very hard to control. That's right.
Yeah,
right.
Yeah.
It can be seen here. Probably know this one, but this one, it can be seen here.
Yeah. So exactly. So it's really important at your like the design or at the design point of view, but also for me, the control point of view, it's really important also.
Exactly. In fact, this optimal design approaches can be done offline. I mean, before you pursue, before you plan to follow a trajectory. So for example, if the robot goes, if the trajectory is just some straight lines, for example, in this case, you can compute offline before you perform the trajectory, and to see what's the optimal joint coordinates to maintain the robot always in a comfortable configuration.
Okay.
Maintain the robot far from the singularities.
Okay.
Yeah, thank you. I'm glad to see that Kefei and C agree on the answer. And I'm glad to see the interaction between the design side and the control side, both being closely related to the architecture of the robot.
Yes, thank you.
Yeah, thank you.
Yeah. Do we have other questions?
I have a question.
Yes, please.
So right now, if I understand correctly, you're using the kinematic redundancy to actuate a gripper. And
exactly.
So how would the kinematic redundancy be used in the mini macro architecture that you're talking about towards the conclusion? Would it still be for a gripper?
So do you mean this one?
Yeah.
Exactly. We still use gripper. So the kinematic redundancy is mainly used to avoid the singularities and then enlarge the orientational workspace. So probably you know the prototype, the 3-degree freedom translational prototype shown in our laboratory in the micro mini system. I don't know whether you remember that robot. That one only has 3 translational degree freedom, and the robot itself has no singularities. That's why the kinematic redundancy is not exploited on that robot. But in this case, this robot has, if we don't, we plan to design a 6-degree freedom parallel robot. But in this case, we will have the temperature singularities that will limit the orientational, the rotational ability. Therefore, that's why we exploited the kinematic redundancy to avoid the singularities. And the gripper is come here as an additional benefit of the kinematic redundancy. The kinematic redundancy at the very beginning is not aimed to use to control the gripper, but it can be used. The redundancy can be used to operate the gripper, but originally it's not designed to control the gripper.
Maybe I could add something here. When we use the kinematic redundancy to operate the gripper, the design is done in such a way that throughout the opening range of the gripper, we know that we will never run into a singularity. So it's completely outside of the singularity configurations. That's the first thing. And the second thing is we have 3 redundant degrees of freedom, and for the gripper we use 2. So we still have 1 redundant degree of freedom that can be used to stay away from singularities.
Yes, you're right.
Good, thank you. And just I'm curious, do you know what kind of force magnitude that you can apply at the gripper right now?
The force magnitude?
Yeah, the gripping force.
Yeah. In fact, we are working on this, and we already have a manuscript to submit next week. It's not given here, but we found a way to control the grasping force. And as can be seen here, we have this gripper has only 2 jaws, and usually, for example, for serial robot, we have a 6-degree freedom force torque sensor mounted on the end effector to measure the force, to measure the external force, and in addition, they also have the load cells on each of the jaw to measure the grasping force. But in our case, we found that from the kinematics, we just need to use only 1 load cell to measure the grasping force between these 2 jaws. And that's all. That's all what we need to compute the joint torques required to control the grasping force. So basically, what I mean is, in general, for a serial robot, we should measure the same degrees of freedom at the Cartesian space and use this information to compute the joint torques. But in our case, we only need the measured force on the Cartesian space. The degrees of the measured force on the Cartesian space is less than the degrees of the joint space. It's partial. What I mean is the Cartesian force and moment is partially measured. And probably you will see the manuscript in several months if we are lucky if the manuscript is lucky to be accepted.
Great, thanks.
Yeah, so Xavier, to answer your question about the gripping force that we can apply now, not very sure. Maybe Thierry has a guess. I don't know. Do you have a guess, Thierry? Or?
I would say 5 to 10 newtons, but it's closely related to the actuators. So it really depends on that.
Yeah, so now because we have a direct right here, so it depends also on the power of the motor. If we have like higher torque from the motor, so we're gonna have like higher force on the gripper, on the gripper. But temporarily now, I set the motor maximum torque of the motor at 1.5 Newton meter. So we can calculate from the Jacobian metric or like the sensitivity. I think.
Yeah, because it's a direct drive transmission, so it's directly related to the actuator torques, which is right now 1.5 Newton meter. Do we have other questions? Okay, maybe everybody's hungry. Before we leave, I just want to say that we'll have another seminar from someone from the robotics lab, Jean-Félix Tremblay-Bugeaud. He will be, actually, he has a paper at the IROS conference, the IEEE IROS, which will take place, I think, at the beginning of November, online. So he will give essentially the same talk, but probablement en français, for the seminars here. By the way, I want to point out that it was announced yesterday or the day before yesterday that the IROS conference will be free. It's online and it will be accessible. It's not going to be in real time. Yeah, I think you log in and you can watch the different presentations because we had to submit presentation videos, but it was announced yesterday or the day before yesterday that it will be free. So it's interesting. If you register, you can have access to the presentations if you're interested. Okay, thank you very much, Kefei. That was a very nice seminar and also a nice opportunity to see each other. So hopefully everyone is doing well. And don't hesitate to reach out. On peut entrer en communication un peu n'importe quand, là, juste pour conserver un peu le beat du labo. Puis, bon, on fonctionne avec ce mode-là en ce moment, puis on espère que éventuellement on pourrait être de retour, mais pour l'instant, c'est ce qu'il faut faire. Donc, on fonctionne de la meilleure façon possible à distance. Alors, merci beaucoup à tous ceux qui se sont joints à nous. Thank you everyone for joining, and we'll keep you posted on the upcoming seminars. OK, merci beaucoup.
Thank you.
Bye bye tout le monde.